Hi class, welcome to Distance Learning Week 2. Today we'll be going over differential equation free response on the AP Calculus AB exam. So we're going to go over full free response questions as they might appear on the AP exam. Last week we focused on solving differential equations. That is going to be part of the free response questions that you will see presented today. Something you should note, your weekly assignment is on AP Classroom, which is on the College Board site. Sorry, that's my kitty. It's the Unit 7 progress check. We're doing this because you have to practice uploading your free response answers in AP Classroom to prepare for the AP exam. The AP exam is on May 12th at 1 p.m. and it is required. Knowledge and skills that we're going to be using today. We are going to sketch a slope field. We are going to write a tangent line. Use implicit differentiation to find d squared y over dx squared, which is the second derivative. We're going to consider relationships between y, dy dx, and d squared y over dx squared based on derivative information. As a hint, you may want your green chart. Unfortunately, my green chart is in the school, so I do not have one. Let's begin. Example 1. Consider the differential equation dy dx equals 2x minus y. So this is my main differential equation. Note that I've been given dy dx, which is like f prime. On the axes provided, sketch a slope field for the given differential equation at the 6 points indicated. Slope in calculus is the derivative, and they gave us the derivative. I'm going to take my derivative, dy dx, and I'm going to plug in the coordinates of each of these points. So let's start with this point right here. This is the point 0, negative 1. 0, negative 1. I'm going to take 0, which is x, and negative 1, which is y, and plug it into dy dx. dy dx evaluated at 0, negative 1 equals 2 times 0 minus negative 1. This becomes 1. The slope at this point here is 1. So I'm going to draw a little line segment that has a slope of positive 1. Something like that. We're going to repeat this process for all 6 of the points. So my second point, I'm going to go, this whole left side is 0, 1. dy dx evaluated at 0, 1 equals 2 times 0 minus 1. This is negative 1. Now I'm going to try to draw a slope that is negative, so my little line segment is decreasing, but has the same relative steepness as the first slope that I drew. My last point here is 0, 2. So I've got the point 0, 2. This work, by the way, you do not need to show this work. I'm just going over it so that you understand where it came from. dy dx evaluated at 0, 2. I'm skipping the notation because I'm out of space. Going to be 2 times 0 minus 2. This is negative 2. I've got a slope of negative 2. I've got to make sure my slope is negative and steeper. Negative and steeper. At this point, you should pause the video and you should try to work out the slopes on the other 3 points. So hopefully by now you have found your slopes for these other 3 points. I'm going to reveal the answers and how they should look. The slope up here was 0. Make sure you have a horizontal line segment. The slope is positive 1. Make sure it's that positive, not too steep. And then the slope is 3. It should be a positive steep line. So your final slope field should look something like that. All right, part B. Find d squared y over dx squared in terms of x and y. Then determine the concavity of all solution curves for the given differential equation in quadrant 2. Give a reason for your answers. d squared y over dx squared is the second derivative. It is the derivative of dy dx. So what I'm going to do is take the dy dx they give me, dy dx equals 2x minus y, and I'm going to differentiate implicitly with respect to x. I'm going to put d dx out front. The derivative of dy dx is d squared y over dx squared equals the derivative of 2x is 2 minus the derivative of y, this is y to the first power. The derivative of y to the first power is 1, y to the 0 power, but watch out, these variables don't match. Implicit times dy dx. The question asked me to put this in terms of x and y. That means that I have to substitute in for dy dx, which was given to me right here. I'm just going to plug in. So d squared y over dx squared equals 2 minus, I need parentheses, 2x minus y, which I can simplify to be 2 minus 2x plus y. So I've answered the first part of the question. Next, determine the concavity of all solution curves for the given differential equation in quadrant 2. Sorry, that's quadrant 2 right there. Okay. Concavity. They're asking me about concavity in the same question they asked me to find the second derivative for a reason. I have to find whether my second derivative is positive or negative, because that will tell me whether f or y is concave up or concave down. Remember, if f double prime is positive, then f is concave up. And if f double prime is negative, then f is concave down. There's a second piece of information here, quadrant 2. I'm going to figure out where quadrant 2 is. 1, 2, 3, 4. Okay, here's quadrant 2. Notice that to get to quadrant 2, I have to go to the left and up. That means that in quadrant 2, the x value is negative and the y value is positive. So let's think about what would happen if I plugged in a negative number for x and a positive number for y into my second derivative. Well, d squared y over dx squared evaluated when x is less than 0 and y is greater than 0 would be, okay, so I'd have 2 minus 2 times some negative number plus some positive number. Minus a negative, that becomes positive. So 2 plus a positive, this is going to be a positive number. D squared y over dx squared is greater than 0 at all points in quadrant 2. So the solution curve is concave up. Continuing on to part 3. Part C. Let y equals f of x be the particular solution to the differential equation with the initial condition f of 2 equals 3. They're just telling you that y is the particular solution. They're not asking you to find it here. The question is, does f have a relative minimum, a relative maximum, or neither at x equals 2? Justify your answer. So I'm going to draw a little picture of f. Okay, a relative minimum. Okay, a relative minimum would look like this if this was f. and a relative maximum would look like that. And neither might be something like that. One thing I should notice is that the slope of f would have to be 0. So, if f had a relative minimum or a relative maximum. The slope does not have to be 0 if it's neither. So what I'm going to do is I'm going to take the coordinate pair 2, 3, where 2 is x and 3 is y, and I am going to plug it in to dy dx. So I'm going to do dy dx evaluated at 2, 3. Now remember, dy dx is this 2x minus y. So 2 times 2 minus 3. 2 times 2 minus 3, this is 4 minus 3. That equals 1. So my slope is 1, but 1 is not 0. Therefore, y equals f of x has neither a max nor min at 2, 3, because dy dx is not 0. The final part to this question is a little strange. Part D says find the values of the constant y, or m and b, for which y equals mx plus b is a solution to the differential equation. So I don't know what y is. However, I do know dy dx. That was given to me. It's 2x minus y. And I do know d squared y over dx squared, which we found was 2 minus 2x plus y. So what I'm going to do here is I'm going to take the information presented in the question and try to manipulate it to be more like the information that I know. So I'm going to start with y equals mx plus b, and I'm going to try to get to dy dx. I'll do that by taking a derivative. So, derivative of y is dy dx. Derivative of mx, well, this would be like derivative of 4x, it'd be 4. Derivative of mx is just m, plus the derivative of b is 0. So dy dx equals m. But dy dx also equals 2x minus y. So I can say that 2x minus y equals m. We're going to go one step further here, though. I'm going to take my derivative dy dx, which is m, and I'm going to go all the way to a second derivative. I'm going to find dy dx equals m, and I'm going to differentiate it. Derivative of dy dx is d squared y over dx squared equals the derivative of m is 0. So I can say that 0 is equal to the second derivative that I already found. So 0 equals 2 minus 2x plus y. I'm going to rearrange this equation so that y is by itself. I'm going to add 2x to both sides, and I'm also going to subtract 2. This yields the result that y equals 2x minus 2. And oh my goodness, we can just see that m is 2 and b is negative 2. Kind of a strange question, but one that we can work out a little bit. So that concludes that question. It was worth 9 points overall. I'll post the scoring guidelines. But I have a second example that I'd like to go over today, which is a real-world problem. Example 2, at the beginning of 2010, a landfill contained 1,400 tons of solid waste. That sounds important. The increasing function W models the total amount of solid waste stored in the landfill. Planners estimate that W will satisfy the differential equation dW dt equals 1/25 of W minus 300 for the next 20 years. W is measured in tons, and T is measured in years. So if W is measured in tons, that means 1,400 is a W. W equals 1,400 tons when, that says measured in years from the start of 2010, and this is at the beginning of 2010, that means T equals 0. Okay. Part A, use the line tangent to W. Line tangent to W at T equals 0 to approximate the amount of solid waste at when the landfill contains at the end of the first 3 months of 2010, which is time T equals 1/4. It's the line tangent to W at T equals 0. So I'm going to ignore this 1/4 for now, and I'm going to make a tangent line. I need 2 pieces of information to write a tangent line. I need a point, and I need a slope. I need a point, and I need a slope. The point is going to be W. Specifically, I need W of 0. I also need a slope. Well, a slope is a derivative. That would be W prime at the same time at 0. W of 0, well, W is 1,400 when T is 0, so W of 0 is 1,400. W prime, another way to say W prime is dW dt. I need dW dt evaluated when, now remember, this 0 is a T, so when T equals 0. I'm going to plug into my dW dt equation, 1/25 times, now I need W. A lot of students make the mistake of plugging in 0 here, but remember 0 is T. W is in fact 1,400, so 1,400 minus 300. You can simplify this. 1,400 minus 300 is 1,100. This is going to be 1,100 over 25, or 44. So I've got 1,444. Now I'm going to write my tangent line. Remember, the tangent line is y minus y1 equals m times x minus x1. So plugging in, I'm going to have y minus, my y1 is 1,400, equals m, which is 44, my slope, x minus 0. Finally, I need to approximate this at time 1/4. Well, time is independent, so W is like your y, T is like your x. T is like your x. So for x, I'm going to plug in 1/4. So what I'm doing is I'm finding W of 1/4. I'm finding W of 1/4. W of 1/4 minus 1,400 is going to be approximately 44 times 1/4 minus 0. You can also add the 1,400 over to the other side in your head if you prefer. So W of 1/4 is approximately 44 times 1/4 plus 1,400, which is 1,411 tons, which is how much waste is in the landfill after 3 months. Part B, find the second derivative in terms of W. Use that second derivative to determine whether your answer in Part A is an under or over estimate of the solid amount of the amount of solid waste that the landfill contains at time 1/4. Okay, we've done this type already. At this point, you could try to pause the video and solve this on your own. But I will go over it here. dW dt equals 1/25 of W minus 300. And I'm going to take a derivative with respect to t. This is d squared W over dt squared equals, now I see a product happening here. So I could use the product rule, or I could go off to the side and I could distribute before I differentiate. That'll make my life a little easier. So this is the same thing as 1/25 W minus 300 over 25 is 12. Okay, so I'm going to differentiate this. So the derivative of 1/25 W is 1/25, and derivative of W is dW dt minus derivative of 12 is 0. So d squared W over dt squared equals 1/25. Now I'm just going to plug in for dW dt. 1/25 times 1/25 times W minus 300. So I'm now going to determine if this is if my 1411 is an under or an overestimate. I can do that by determining concavity. If I plug in some number for W, it's going to be larger than 300. So d squared W over dt squared is going to be greater than 0 for all times. Between t equals 0 and t equals 1/4. This means that W is concave up. I'm going to draw a little concave up function. If I draw a tangent line on a concave up function, notice how the tangent line is below the curve. So I can say, therefore, my estimate is an underestimate. Finally, part C, find the particular solution W to the differential equation dW dt equals 1/25 W minus 300 with the initial condition W of 0 equals 1400. This is the same process that we learned last week. At this point, I'm going to stop my recording. I will work out the problem, and it will appear at the end of this video, but I will not record that section of the video. So at this time, you can continue to work part C, pause the video, and come back for the solution. Hopefully by this point you have paused your video and tried to work out this part of the problem on your own. I'm going to reveal the answer. We can see that our final answer through the process of separating and integrating and plugging in our initial condition of 0, 1400, we get that W is 1100 e to the 1/25t plus 300. I hope you all have been able to follow what has happened here. Thank you for watching.